Right now, somewhere in the Milky Way, there is a dead star no bigger than the Earth. That weighs more than the Sun. A single teaspoon of its material, scooped from its surface, would weigh approximately 5 tons. 5 tons in a teaspoon. That is roughly the weight of a full-grown adult elephant, compressed into a space you could balance on your fingertip. And if you could somehow set that teaspoon down on the ground here on Earth, it would punch through the floor, through the foundation, and keep going, boring down through the crust like a bullet through paper. This bizarre, impossibly dense object is called a white dwarf, and it is what our own sun will one day become. Not as some distant speculation, not as one possibility among many. This is the fate that awaits our star. It is written in the equations of physics with the same certainty as tomorrow's sunrise. And the journey to get there, from the warm yellow star that lights your morning to that tiny, crystallizing ember drifting alone through the galaxy, is one of the most dramatic and beautiful stories in all of astronomy. It involves hidden explosions that briefly outshine the entire Milky Way. It involves a star swelling to hundreds of times its current diameter, large enough to swallow whole planets. It involves the creation of carbon and oxygen, the very elements your body is built from, forged at 100 million degrees in a nuclear furnace deep inside a dying star. And at the end, after billions of years of slow transformation, the star simply fades, quietly, gently, into the longest night the universe has ever known. This is the story of how stars like our sun live, age, and die. The story of red giants and white dwarfs. But before we can talk about how a star dies, we need to understand how it lives. And to do that, we need to go back to the very beginning, to a cold, dark cloud of gas drifting between the stars. The space between the stars is not truly empty. It is filled, thinly but pervasively, with what astronomers call the interstellar medium, a sparse mixture of gas and microscopic dust grains. Most of this gas is hydrogen, the simplest and most abundant element in the universe, with smaller amounts of helium and trace quantities of heavier elements. In some regions, this material gathers into vast, dense concentrations called molecular clouds. These clouds are enormous. Some span hundreds of light years, containing enough raw material to build thousands or even millions of stars. And they are cold. Deep inside, where the gas is shielded from the warming radiation of nearby stars, temperatures can drop to just 10 or 20 degrees above absolute zero. At these temperatures, hydrogen atoms bond together into hydrogen molecules, which is why they are called molecular clouds. For most of their existence, these clouds drift quietly through the galaxy, held together by their own gravity, but prevented from collapsing by internal gas pressure, magnetic fields, and the turbulent motions of the gas itself. The cloud is in a kind of uneasy equilibrium, balanced on a knife's edge. But sometimes, a disturbance upsets that balance. Perhaps a shockwave from a nearby supernova explosion ripples through the cloud, compressing it. Perhaps the gravitational tug of a passing star gives it a nudge. Perhaps two clouds collide, or the cloud passes through one of the dense spiral arms of the galaxy and is squeezed by the higher density of material there. Whatever the trigger, small regions of the cloud begin to collapse under their own gravity. Once the collapse begins, it feeds on itself. As the material falls inward, the density at the center increases, strengthens the gravitational pull, which draws in more material, which increases the density further. It is a runaway process, and it happens with surprising speed, at least by cosmic standards. At the center of this collapsing region, a dense knot of gas forms, a protostar. It is not yet a true star. It does not shine by nuclear fusion. It glows only because the gravitational energy of the infalling material is being converted to heat. As more and more material piles on, the pressure and temperature at the center climbs steadily. The protostar grows hotter and more luminous. It may be surrounded by a swirling disk of gas and dust, the leftover material that did not fall directly onto the central object. This disk is the raw material from which planets will later form. And then, at a certain point, the temperature at the very center of the protostar reaches a critical threshold, roughly 15 million degrees Kelvin. At this temperature, the hydrogen nuclei, which are simply protons, are moving so fast and are packed so closely together that they begin to overcome their natural electromagnetic repulsion. Protons carry positive electric charge, and like charges repel. Under normal circumstances, two protons would push each other apart long before they could get close enough to interact via the nuclear force. But at 15 million degrees, the thermal energy is so enormous that the protons can slam together with enough violence to merge. Through a series of steps called the proton-proton chain, 4 hydrogen nuclei are welded together to produce a single helium-4 nucleus, 2 positrons, 2 neutrinos, and a burst of energy in the form of gamma-ray photons. In this process, a tiny fraction of the original mass of the 4 hydrogen nuclei is not present in the final helium nucleus. It has been converted into energy in accordance with Einstein's equation, E equals mc squared. The fraction is small, about 0.7% of the total mass involved. But when you multiply that tiny fraction by the enormous number of reactions happening every second, the total energy output is stupendous. Our sun, for example, converts roughly 620 million metric tons of hydrogen into roughly 616 million metric tons of helium every single second. The missing 4 million metric tons are transformed entirely into energy, radiated outward as light and heat. This is the engine that powers every star in the universe, and it has been running inside our sun for roughly 4.5 billion years. The energy released by nuclear fusion creates an outward pressure, pushing against the inward pull of gravity. And gravity pushes back, squeezing the star's material inward. When these two forces are in balance, the star reaches a state called hydrostatic equilibrium. It neither expands nor contracts. It just sits there, burning hydrogen in its core, shining steadily, balanced like a ball on the tip of a fountain jet. This balanced state is what defines a main sequence star. It is the longest and most stable phase of a star's life, the period during which it spends most of its time. For a star like our sun, the main sequence lasts about 10 billion years. For stars much more massive than the sun, perhaps 10 or 20 times heavier, the main sequence can be as short as a few million years. These massive stars burn through their hydrogen fuel with reckless speed, living fast and dying young. At the other extreme, the smallest red dwarf stars, with perhaps 1/10 of the sun's mass, burn so slowly and so frugally that their main sequence lifetimes stretch to 1 trillion years or more, far longer than the current age of the universe. Some red dwarfs that formed shortly after the Big Bang are still on the main sequence today, having barely begun their supply of hydrogen. Our Sun, sitting roughly in the middle of this range, is currently about 4.5 billion years old. It is approximately halfway through its main sequence lifetime. It is a middle-aged star, not young, not old, burning steadily and reliably. During its time on the main sequence, the Sun is not perfectly constant. As hydrogen is converted to helium in the core, the chemical composition of the core gradually changes. Helium, being heavier than hydrogen, settles toward the center. The core slowly becomes denser, contracts slightly, and heats up. This modest increase in core temperature accelerates the fusion rate, causing the Sun to grow slowly brighter over time, at a rate of roughly 1% per 100 million years. When the Sun first arrived on the main sequence, it was about 30% dimmer than it is today. And in 1 billion years, it will be roughly 10% brighter. These changes are imperceptible on human timescales, but over geological time, they have profound consequences. This slow brightening of the Sun has had real consequences for the history of life on Earth. Early in our planet's history, when the Sun was 30% dimmer, Earth should have been a frozen snowball, and yet, geological evidence clearly shows that liquid water existed on Earth's surface even then. This is known as the faint young sun paradox, and it has been a subject of intense scientific debate for decades. The most likely explanation involves a stronger greenhouse effect in the early atmosphere, probably from higher concentrations of carbon dioxide and methane, which compensated for the weaker sunlight and kept the surface warm enough for liquid oceans. As the Sun slowly brightened over billions of years, Earth's climate adjusted. Geological and biological processes gradually drew down the greenhouse gases to maintain habitable temperatures. It is a delicate dance between star and planet, played out over cosmic time, and one that cannot last forever. Astronomers visualize the lives of stars using a tool called the Hertzsprung-Russell diagram, or HR diagram, named after the Danish astronomer Ejnar Hertzsprung and the American astronomer Henry Norris Russell, who independently developed it in the early 20th century. The diagram plots the brightness of a star on the vertical axis against its surface temperature on the horizontal axis. When you plot a large number of stars on this diagram, a striking pattern emerges. The vast majority fall along a diagonal band running from hot, bright blue-white stars in the upper left to cool, dim red stars in the lower right. This band is the main sequence. Stars spend most of their lives on this band, and their position on it is determined almost entirely by their mass. More massive stars are hotter and brighter, occupying the upper left. Less massive stars are cooler and dimmer, sitting in the lower right. The Sun is a modest, middle-of-the-road star, positioned roughly in the center of the main sequence. But the HR diagram also reveals what happens to stars when they leave the main sequence. Above and to the right, there is a scattering of very bright, cool stars, the red giants and red supergiants. Below and to the left, there is a cluster of very hot, dim stars, the white dwarfs. These are the endpoints and way stations of stellar evolution. And by studying the HR diagram, astronomers can read the life story of a star from birth to death, the journey that a sun-like star takes across this diagram, from the main sequence to the red giant branch, across the horizontal branch, up the asymptotic giant branch, and finally down to the white dwarf cooling track, traces the arc of an entire stellar lifetime. It is one of the great achievements of 20th century astrophysics to have deciphered this journey. There is another dimension to the sun's internal workings worth understanding before we discuss its eventual death. The energy produced by nuclear fusion in the core does not travel directly to the surface as light. The journey from core to surface is surprisingly long and torturous. In the innermost regions, the energy is transported by radiation. Photons emitted by the fusion reactions bounce from atom to atom, absorbed and re-emitted countless times. The density is so high that each photon travels only a fraction of a centimeter before being absorbed and re-radiated in a random direction. It is like trying to walk across a room packed wall-to-wall with people. This radiative zone extends from the core to roughly 70% of the sun's radius. Because of the constant scattering, it takes an extraordinarily long time for energy to diffuse outward. Estimates suggest that a photon produced in the sun's core takes somewhere between 10,000 and 170,000 years to reach the edge of the radiative zone. The light that warms your face today was produced in the core during the last ice age, or perhaps further back in human prehistory. Above the radiative zone, the sun's structure changes. The temperature drops to the point where the material becomes more opaque, and instead of radiation, heat is transported by convection. Hot gas rises toward the surface, cools, and sinks back down, like water boiling in a pot. This convective zone extends from roughly 70% of the sun's radius all the way to the visible surface, the photosphere. The convective cells are visible on the sun's surface as a pattern of granulation, millions of roughly Earth-sized cells of bright, rising gas surrounded by darker lanes of cooler, sinking gas. Understanding this internal structure, the core, the radiative zone, the convective zone, and the photosphere, is essential for understanding what happens when the fuel runs out, because the crisis does not begin everywhere in the star at once. It begins in one very specific place, the core. But eventually, the fuel runs out. And when it does, everything changes. The core of the sun is not the entire sun. It is only the innermost region, extending perhaps to about a quarter of the star's radius, where the temperature and pressure are high enough for hydrogen fusion to occur. The rest of the star, the vast majority of its volume, contains enormous quantities of hydrogen. But that hydrogen is too cool and too diffuse to undergo fusion. It just sits there, inert, pressing down on the core with its weight. And over the course of billions of years, the hydrogen in the core is steadily consumed. Each second, 620 million metric tons are transformed. It sounds like an enormous rate, and it is. But the core contains an incomprehensible quantity of material. It takes billions of years to work through it all. When the core finally exhausts its hydrogen supply, the nuclear furnace that has sustained the star for its entire main sequence life sputters and dies. The outward pressure that had been holding gravity at bay begins to weaken. Gravity that patient, unyielding force seizes the opportunity. The core, now composed almost entirely of helium ash, begins to contract. Here is where the story takes an unexpected turn. You might think that a star running out of fuel would simply dim and cool, growing fainter and smaller as it exhausted its remaining energy. But that is not what happens, not even close. Instead, the star begins to do something almost paradoxical. It gets bigger, vastly, spectacularly bigger, and brighter, far brighter than it has ever been. The reason lies in what happens as the helium core contracts. Compressing a gas heats it up. This is a basic principle of physics. So, as the core shrinks under gravity, it grows hotter. The core itself cannot yet fuse helium. That requires temperatures far higher than the core currently possesses. But the heat radiating outward from the contracting core reaches the layer of hydrogen immediately above it. This hydrogen has been sitting there for billions of years, too cool to fuse, but now, heated by the shrinking core below, it reaches the ignition temperature. A shell of hydrogen surrounding the inert helium core bursts into fusion. This hydrogen shell burning is actually more energetic than the core burning that preceded it. The shell is at higher temperatures and higher pressures than the old core was, and the fusion reactions proceed with greater vigor. The total energy output of the star increases dramatically. But this energy has to go somewhere. It pushes outward, inflating the outer layers of the star like a balloon. Astrophysicists describe this with what they call the mirror principle. When the core contracts, the envelope expands. The inner regions of the star shrink while the outer regions swell. The physical details are complex, involving the subtle interplay of gravitational and thermal energy in a star with a shell-burning structure. But the result is unmistakable. The star begins to bloat. Its outer layers push outward, ballooning to immense proportions. And as they expand, they cool, just as steam cools when it escapes a kettle. The surface temperature drops from perhaps 5,800 degrees down to around 3,500 degrees or lower. The color shifts from yellow-white to a deep, warm orange red. A red giant is born. The scale of this transformation defies easy comprehension. Our sun, currently about 864,000 miles in diameter, will expand to perhaps 100 to 250 times that size during its red giant phase. At its most extreme, it could reach a diameter of over 200 million miles, large enough that if you placed it where the sun is now, its surface would extend to the orbit of Mars or beyond. The star that once sat comfortably within a single astronomical unit now fills a volume millions of times larger than before. And despite the cooler surface temperature, the sheer immensity of the star makes it extraordinarily luminous. A red giant sun would shine roughly 1,000 to several thousand times brighter than it does today. To put this in more concrete terms, imagine you could somehow shrink the sun down to the size of a basketball. At that scale, the Earth would be a tiny grain of sand, about 2 millimeters in diameter, orbiting roughly 80 feet away. When the sun becomes a red giant, the basketball would swell to the size of an entire football field. The grain of sand that was Earth, still orbiting at the same distance, would now be inside the bloated star, engulfed by its outermost layers. The transformation from a main sequence star to red giant is like watching a single candle flame expand to fill an entire room. The red giant's outer atmosphere is remarkably different from the surface of a main sequence star. It is vast, diffuse, and tenuous. There is no sharp boundary between the star and the surrounding space. Instead, the density decreases gradually, trailing off into a wind of expelled particles that slowly carry mass away from the star. The interior of the red giant is dominated by enormous convective cells, columns of hot gas rising from deeper layers and cooler gas sinking back down, like the bubbling of a pot of thick soup on a stove. But these convective cells are not small. In a red giant, a single convective cell can be larger than the entire current sun. The surface patterns created by these convective cells make red giant variable stars. Their brightness fluctuates slightly as the cells rise, expand, and sink, causing subtle changes in the star's total light output. This variability is typically small, just a few percent, and irregular, making red giants classified as slow, irregular variables. The color of a red giant, despite the name, is not truly red. To the naked eye, most red giants appear orange, amber, or warm golden. The term red in the name refers to the red end of the stellar temperature spectrum. Stars are classified on a temperature scale using spectral types designated by the letters O, B, A, F, G, K, and M. Running from the hottest blue-white stars to the coolest red ones, red giants typically fall into the K and M spectral classes, with surface temperatures between roughly 3,000 and 5,000 degrees Kelvin. Our Sun, by comparison, is a G-type star with a surface temperature of about 5,800 degrees. When you look at Aldebaran or Arcturus, what you see is a warm, coppery orange glow, distinctly different from the blue-white sparkle of a young, hot star like Sirius or Vega. And you can see these stars tonight if you know where to look. Some of the most recognizable stars in the sky are red giants. Aldebaran, the fiery eye of Taurus the Bull, is a classic example, located about 65 light-years from Earth. Aldebaran is a red giant that has exhausted the hydrogen in its core and is currently burning hydrogen in a shell around a helium-rich center. It is roughly 44 times the Sun's diameter. Despite having only about 16% more mass than the Sun, it shines with over 400 times the Sun's luminosity. Its surface temperature is a relatively cool 3,900 degrees Kelvin, giving it its distinctive orange-red color. The name Aldebaran comes from the Arabic al-Dabaran, meaning the follower, because it appears to follow the Pleiades star cluster across the sky. It was one of the stars whose movement across the sky helped the English astronomer Edmund Halley discover the phenomenon of stellar proper motion in 1718, proving that the so-called fixed stars are not truly fixed, but move through space on their own individual trajectories. Over the past 2,000 years, Aldebaran has shifted its apparent position by roughly a quarter of the diameter of the full moon, a tiny drift, but enough for Halley to detect by comparing his observations with records left by Ptolemy and other ancient astronomers. Aldebaran's estimated age is roughly 6.4 billion years, making it about 2 billion years older than our Sun. It has already been through the same main sequence phase that our Sun is currently enjoying. burned through its core hydrogen and is now living out its years as a red giant. Looking at Aldebaran is, in a very real sense, looking at a preview of what our own sun will become. Arcturus, the brightest star in the northern hemisphere and the fourth brightest star overall, is another red giant. It sits in the constellation Bootes, about 37 light-years from Earth. It is roughly 25 times the Sun's diameter and produces about 170 times the Sun's luminosity. Arcturus is estimated to be around 7 billion years old, significantly older than our Sun, and has long since left the main sequence behind. In 1933, light from Arcturus was used to trigger the opening of the Chicago World's Fair, because Arcturus was then believed to be about 40 light-years away, and the previous fair had been held 40 years earlier. The light captured was thought to have left the star at the time of the earlier fair. It was a romantic notion, linking the passage of starlight to the passage of human time. The actual distance, later refined to 37 light-years, does not quite match, but the symbolism endures. Mira, a pulsating red giant in the constellation Cetus the Whale, provides a dramatic example of how unstable the red giant phase can be. Mira varies in brightness over a cycle of about 330 days. At its peak, it is visible to the naked eye. At its faintest, it practically disappears, requiring a telescope to detect. This pulsation is driven by instabilities in the star's outer layers, which expand and contract rhythmically as the star struggles to maintain equilibrium. In 2007, astronomers discovered that Mira is shedding material so rapidly that it has left a tail of gas behind it, stretching 13 light-years through space, the longest such feature ever observed around a star, like a comet's tail, but on an unimaginably grander scale. The material in this tail contains carbon and other heavy elements that Mira has synthesized and expelled over the past 30,000 years, a visible record of the star's final contributions to the interstellar medium. And then there is Betelgeuse, the famous red star that marks the left shoulder of Orion. Betelgeuse is not technically a red giant in the same category as the stars we have been discussing. It is far more massive, perhaps 14 to 20 times the mass of the Sun, which puts it in the red supergiant category. And its death will be far more violent, ending not as a white dwarf, but as a supernova. But it illustrates the same basic processes of stellar aging on a grander scale. Betelgeuse has swollen to a diameter roughly 700 to 1,000 times that of the Sun. If placed at the center of our solar system, its surface would extend past the orbit of Jupiter. In late 2019 and early 2020, Betelgeuse made international headlines when it dimmed dramatically, dropping from one of the top 10 brightest stars in the sky to below the top 20. Speculation ran wild that the star might be about to explode. In reality, astronomers determined that the dimming was most likely caused by a large cloud of dust ejected from the star's surface, temporarily blocking some of its light from our perspective. The episode was a vivid reminder of how dynamic and unpredictable the final stages of stellar evolution can be. Interestingly, research published in 2022 using historical records from ancient Greek and Roman astronomers found evidence that Betelgeuse was described as yellow-orange just 2,000 years ago, suggesting it has undergone significant color evolution in a remarkably short time by astronomical standards, transitioning from the blue end of its evolutionary loop to its current deep red supergiant state within recorded human history. These are not exotic, one-in-a-million objects. Red giants are an entirely normal phase in the life of every star, between roughly 1/3 and 8 times the mass of the Sun. Since that mass range covers the vast majority of all stars that have ever formed, red giants are among the most common types of evolved stars in the galaxy. There are millions of them in the Milky Way right now, quietly swelling and glowing in the later stages of their lives. It is worth noting that the transition from a main sequence star to a full-fledged red giant is not instantaneous. There is an intermediate phase called the subgiant phase, during which the star gradually migrates across the HR diagram. During this phase, the helium core is growing, but has not yet reached the temperatures needed for new fusion processes. The hydrogen shell burning is ramping up, and the outer layers are beginning to expand, but the star has not yet reached its full red giant dimensions. The subgiant phase can last hundreds of millions of years for a sun-like star, a gradual swelling and cooling that would be imperceptible within a single human lifetime, or even across the span of an entire civilization. The star is dying, but it is doing so with exquisite slowness. As the star continues to ascend the red giant branch of the HR diagram, growing larger and more luminous, its internal structure becomes increasingly extreme. The helium core, perhaps no bigger than the planet Earth, is unimaginably dense and hot, surrounded by a thin, furiously burning shell of hydrogen, which is in turn surrounded by an enormous, low-density envelope of gas, extending out to hundreds of millions of miles. The contrast between the core and the envelope is staggering. The core density might be 1,000,000 times that of water, while the outermost layers of the star are thinner than the best laboratory vacuum achievable on Earth. If you could somehow stand inside the outer envelope of a red giant, you would see virtually nothing. The gas would be so thin that it would be nearly transparent. You might not even realize you were inside a star at all, except for the faint, warm glow of light filtering in from far below. The red giant phase also brings a phenomenon called the first dredge-up. As the star's convective envelope deepens, it reaches down into regions that were previously part of the radiative interior, regions where some nuclear processing has occurred during the main sequence, material that has been partially processed by the CNO cycle, enriched in nitrogen, and the heavier isotope of carbon, carbon-13, is mixed up to the surface for the first time. Spectroscopic observations of red giant atmospheres confirm this. Red giants show lower ratios of carbon-12 to carbon-13 compared to main sequence stars, a chemical fingerprint of the dredge-up process. This is the first time that the star's internal nuclear cookery becomes visible from the outside, like a chef finally serving a dish that has been simmering for billions of years. At a certain point on the red giant branch, the deepening convection zone reaches its maximum extent and then begins to recede. This creates a brief pause in the star's brightening, a slight bump in the luminosity evolution known as the luminosity bump. It is a subtle feature, but astronomers have observed it in the populations of red giants in globular clusters, where thousands of stars at different evolutionary stages can be studied simultaneously. The luminosity bump is a small signature of an enormous internal event, the retreat of the convective boundary and the smoothing of chemical composition gradients left behind by the first dredge-up. But the red giant phase is not a single event. It is a sequence of increasingly dramatic transformations. And the first truly astonishing event in this sequence is something that occurs entirely out of sight, a hidden detonation of almost incomprehensible violence, buried deep within the star. As the red giant continues to burn hydrogen in a shell around its helium core, that core keeps growing heavier. Every second, more helium ash is deposited onto it from the burning shell above. And as the core gains mass, it contracts further under gravity, growing denser and hotter still. But the matter inside this core is behaving in a way that is fundamentally unlike anything in our everyday experience. It is becoming degenerate. This word, in the context of physics, has a very specific meaning. It refers to a state of matter in which the rules of quantum mechanics dominate over classical thermodynamics. In a normal gas, when you heat it, the pressure increases and the gas expands. When you compress it, it pushes back with greater force, proportional to its temperature. There is a natural feedback loop. Increasing temperature leads to expansion, which leads to cooling, which limits further reactions. This is the thermostat that keeps main sequence stars stable. But in degenerate matter, this thermostat is broken. In the core of a low-mass red giant, the electrons are squeezed together so tightly that they enter a quantum mechanical state governed by the Pauli exclusion principle. This principle, formulated by the Austrian physicist Wolfgang Pauli in 1925, states that no two fermions, a class of particles that includes electrons, protons, and neutrons, can occupy the same quantum state at the same time. You can think of it as a cosmic rule book. Each electron must have a unique combination of properties, including its energy level, its position, and its spin. In normal matter, there is plenty of room for every electron to find its own distinct state. But in the incredibly dense core of a red giant, where the density can reach millions of times the density of water, the lower energy states are completely filled. Every available seat at the lower levels is taken. Electrons are forced into higher and higher energy states, moving faster and faster, simply because there is no room at the bottom. These fast-moving electrons create a pressure, electron degeneracy pressure, that resists further compression. Crucially, this pressure depends only on the density of the material, not on its temperature. You can heat degenerate matter to extraordinary temperatures without it expanding. The electrons do not care about the temperature. They are already moving as fast as quantum mechanics demands, given the density, and no amount of additional heat will change that. This creates a dangerous situation. The helium core, heated by the ongoing contraction and by the shell burning above, grows hotter and hotter. Under normal circumstances, this rising temperature would cause the core to expand, cooling it down and regulating the reaction rate. But in a degenerate core, the temperature rises without the core expanding. There is no release valve. No cooling mechanism, just a steadily climbing thermometer inside a container that refuses to swell. When the core temperature finally reaches approximately 100 million degrees Kelvin, a new nuclear reaction becomes possible for the first time. At this extraordinary temperature, helium nuclei, each consisting of 2 protons and 2 neutrons, begin to fuse together. The process is called the triple alpha process because helium-4 nuclei are also known as alpha particles in nuclear physics. In the first step, 2 helium nuclei collide and momentarily form an extremely unstable isotope of beryllium, beryllium-8. This nucleus is so unstable that it lasts for only about a 10 billionth of a second before disintegrating back into 2 helium nuclei. But if, during that infinitesimally brief window, a third helium nucleus collides with the beryllium-8, a stable carbon-12 nucleus is formed. This reaction is possible only because the temperature is so outrageously high that there are enough energetic collisions happening every fraction of a second for the triple collision to occur with meaningful frequency. Under normal conditions, when the triple alpha process begins, the energy it releases would cause the core to expand slightly, cooling it down and moderating the reaction. A gentle, controlled burn would commence, and the star would settle into a new equilibrium. But in a degenerate core, this safety mechanism does not exist. The temperature rises, the reaction rate increases. The increased reaction rate produces more energy, which raises the temperature further, which accelerates the reaction even more. It is a thermonuclear runaway, a bomb. This is the helium flash. In the span of just a few minutes, the entire degenerate helium core ignites almost simultaneously in a cascade of nuclear fusion. The peak energy output during those few minutes is staggering. Estimates suggest that the helium flash produces energy at a rate comparable to the luminosity of the entire Milky Way galaxy. Roughly 100 billion stars worth of power, generated from a core smaller than the Earth, compressed into an interval shorter than the time it takes to brew a cup of coffee. And yet, astonishingly, you would never know it happened. Not from the outside. The helium flash takes place deep inside the star, buried under layer upon layer of material. The incredible burst of energy does not reach the surface. Instead, it is absorbed entirely within the core itself. The energy goes into lifting the degeneracy of the electrons, allowing the core to expand for the first time in eons. As the core swells, it cools, and the runaway reaction subsides. Within a relatively short time, the core settles into a new state, non-degenerate, steadily fusing helium into carbon at a controlled, sustainable rate. The transition is so deeply buried that an astronomer observing the red giant from the outside would notice virtually no change in its outward appearance during the flash. The helium flash is one of the most violent events in the life of a low-mass star. Yet it passes in near-perfect silence, hidden from the universe behind a curtain of stellar material billions of tons thick. It is a strange and humbling thought. The most energetic event in a star's post-main sequence evolution, until the very end, occurs completely invisibly. If a civilization lived on a planet orbiting a red giant about to undergo its helium flash, they would have no warning, no brightening, no shaking of the heavens. The flash would happen, the core would rearrange itself, and life, if there were any, would go on as if nothing had occurred. Only the slow, gradual changes in the star's luminosity and temperature over the following millions of years would hint that something fundamental had shifted deep in the heart of their sun. It is also worth noting that the helium flash occurs only in stars below about 2 solar masses. In more massive stars, the helium core reaches fusion temperatures before it becomes degenerate. For these heavier stars, helium ignition is a calm, orderly process, more like turning on a furnace than setting off a bomb. The core heats up, helium fusion begins gently, and the star smoothly transitions to the horizontal branch. There is no flash, no runaway, no drama. The mass of the star determines which path it takes. A quiet ignition for the heavy ones, a hidden thermonuclear catastrophe for the lighter ones, like our sun. The dividing line, at roughly 2 solar masses, is one of the key thresholds in stellar astrophysics, separating 2 fundamentally different experiences of old age. After the helium flash resolves the crisis of the degenerate core, the star finds itself in a new and relatively stable configuration. The core, no longer degenerate, is now steadily converting helium into carbon through the triple alpha process. Hydrogen continues to burn in a shell around the core. The star has been given a reprieve, a second wind, a new source of fuel to maintain its internal balance. In response to the renewed core burning, the star adjusts its structure. It contracts somewhat from its bloated red giant dimensions. Its surface temperature increases. Its overall luminosity actually drops slightly compared to the tip of the red giant branch, the point of maximum brightness before the helium flash. On the Hertzsprung-Russell diagram, the star moves to the left and downward, settling onto a region called the horizontal branch. In globular clusters, where astronomers can observe thousands of stars at different stages of evolution, all at the same distance, the horizontal branch shows up as a prominent feature, a nearly horizontal line of stars, all fusing helium in their cores at a variety of surface temperatures but similar luminosities. During this phase, the core is busily at work, constructing some of the most important elements in the universe. The primary product of the triple alpha process is carbon-12, a nucleus with 6 protons and 6 neutrons. But the process does not stop there. A freshly minted carbon-12 nucleus, still sitting in the intense heat of the core, can capture an additional helium-4 nucleus to produce oxygen-16, 8 protons and 8 neutrons. The competition between these 2 reactions, carbon production and carbon destruction into oxygen, determines the final composition of the core. In general, the core ends up as a roughly equal mixture of carbon and oxygen, though the exact ratio depends on the star's mass and the details of its internal structure. These 2 elements are worth pausing to consider. Carbon is the 4th most abundant element in the universe by mass, and it is the foundation of all known organic chemistry. Every protein, every strand of DNA, every sugar and fat molecule in every living thing on Earth is built around a framework of carbon atoms. Oxygen is the 3rd most abundant element and is essential for water, for breathable atmospheres, and for the oxidation reactions that power aerobic life. And both of them are being created right now, at this very moment, inside the fusing cores of horizontal branch stars throughout the galaxy. The carbon atoms in your body were once part of a helium-fusing core inside a star, not in some vague, poetic, metaphorical sense. Literally, those specific atoms were forged in a nuclear furnace at 100 million degrees, deep inside a red giant that lived and died billions of years ago, before the sun existed, before the Earth existed. When that star shed its outer layers, those carbon atoms were scattered into space. They drifted through the interstellar medium, were incorporated into a molecular cloud, and eventually found their way into the collapsing knot of gas that became our solar system. You are, in the most concrete and physical sense possible, made of material that was once inside a star. The calcium in your bones, the iron in your blood, the carbon in your muscles, all of it forged in the hearts of dying stars, scattered into space and reassembled into you. The horizontal branch phase is relatively brief by stellar standards. For a star of roughly solar mass, it lasts approximately 100 million years. That sounds long, and by human reckoning it is, but compared to the 10 billion year main sequence lifetime, it is merely a flash. During this time, the star burns steadily through its helium supply, building up the carbon-oxygen core at the center. The competition between carbon production and oxygen production in the core is one of the great unresolved puzzles in stellar astrophysics. The ratio of carbon to oxygen in the final white dwarf depends sensitively on the rate of the reaction that converts carbon into oxygen by adding another helium nucleus. This reaction rate has been notoriously difficult to measure in the laboratory because it occurs at energies far below what can be easily produced in particle accelerators. Small changes in this rate lead to large changes in the predicted carbon-to-oxygen ratio of white dwarfs, and in the abundances of these elements scattered into space when the star dies. It is one of those cases where the fate of entire solar systems, the composition of future planets, the availability of carbon for future life, hinges on a single nuclear cross-section measured in units of trillionths of a square centimeter. The existence of life on Earth, and perhaps life anywhere in the universe, depends on a remarkable coincidence first recognized by the English astronomer Fred Hoyle in the 1950s. Hoyle realized that the triple alpha process, in which 3 helium nuclei fuse to form carbon, should be extremely unlikely if the relevant nuclear energy levels did not align in a very specific way. He predicted that the carbon-12 nucleus must have a particular excited state, a resonance, at just the right energy to make the reaction proceed fast enough to produce significant amounts of carbon in stars. This resonance was subsequently found experimentally, exactly where Hoyle predicted. Without it, the universe would contain almost no carbon, and carbon-based life would be impossible. It is one of the most celebrated examples of a successful theoretical prediction in nuclear physics, and it carries a philosophical weight that extends far beyond astrophysics. The existence of the atoms in your body depends on the precise value of a quantum energy level inside the carbon nucleus, a level that happens to fall in the one narrow window that makes carbon production possible. And when the helium is finally exhausted, the star faces yet another crisis. When the helium in the core is gone, the pattern repeats, but with a new twist. The carbon-oxygen core, deprived of its energy source, begins to contract under gravity, just as the helium core did before it. Heat from the contraction raises the temperature of the surrounding layers. A shell of helium ignites around the carbon-oxygen core. Farther out, hydrogen continues to fuse in its own shell. The star now has a layered structure, an inert carbon-oxygen core, surrounded by a helium-burning shell, surrounded by a hydrogen-burning shell, surrounded by an enormous, diffuse envelope of gas. The star is now on the asymptotic giant branch, commonly abbreviated AGB. This is the second red giant phase, and it is in many ways even more dramatic than the first. The star swells to truly colossal sizes, its radius reaching hundreds of times the radius of the sun. Its luminosity skyrockets to thousands, or even tens of thousands, of times the sun's output. AGB stars are among the brightest individual stars in any galaxy, blazing beacons visible across millions of light years. If you could see one up close, it would be an awe-inspiring, even terrifying sight. A vast, churning sphere of gas, its surface roiling with convective cells the size of entire stellar systems, its diffuse outer layers gradually bleeding into the surrounding void. But the AGB phase is also profoundly unstable. The two-shell burning structure, with its helium and hydrogen shells nested one inside the other, creates a peculiar and violent oscillation. The helium shell does not burn steadily. Instead, it goes through cycles of quiescence and explosive activity called thermal pulses. The mechanism works like this. The hydrogen shell burns continuously, steadily depositing helium ash onto the thin helium shell below. As helium accumulates, the helium shell grows heavier and denser. Its temperature creeps upward. Eventually, the accumulated helium reaches a critical threshold of mass and temperature, and it ignites in a sudden, intense burst of fusion. This pulse of helium burning produces a tremendous rush of energy, which briefly disrupts the hydrogen shell above, shutting it down. The star's luminosity fluctuates. Its outer layers shudder. Then, as the helium shell burns through its accumulated fuel, it quiets down. The hydrogen shell reignites. The cycle begins again. These thermal pulses occur with a cadence of roughly 10,000 to 100,000 years, depending on the mass of the star. Each pulse is accompanied by vigorous convective mixing, stirring material from deep within the star up toward the surface in events called dredge-ups. The dredge-ups are critically important because they transport freshly synthesized heavy elements from the star's interior to its outer atmosphere. Carbon, forged in the helium-burning regions, is carried to the surface. Nitrogen, created through the CNO cycle in the hydrogen-burning shell, comes along for the ride. Even heavier elements, produced through a slow process of neutron capture, known as the S process, short for slow neutron capture, are dredged up as well. The S process creates elements like barium, strontium, zirconium, and even lead, atom by atom, as free neutrons are gradually absorbed by nuclei in the intershell region between the two burning shells. These newly heavy atoms are then mixed to the surface by convective currents during thermal pulses. In some AGB stars, the dredge-up of carbon is so efficient that the surface becomes carbon-rich. The number of carbon atoms exceeds the number of oxygen atoms. These are carbon stars, and they are among the reddest objects visible in the sky. Their atmospheres are filled with carbon-bearing molecules like C2, diatomic carbon, CN, cyanogen, and CH, methylidine, which absorb blue and green light very efficiently, giving the star a deep, smoldering crimson appearance. Carbon stars are also surrounded by thick shells of carbonaceous dust, tiny grains of soot-like material that form in the cooling outer atmosphere and are blown outward by the stellar wind. This dust is among the raw materials from which new planetary systems will eventually be built. The thermal pulses also drive increasingly intense mass loss. Each pulse sends a shockwave through the star's extended atmosphere, accelerating the stellar wind that continuously carries material away from the surface. AGB stars shed mass at rates that are almost difficult to believe. While the Sun currently loses mass at a rate of roughly 2 to 3 times 10 to the negative 14 solar masses per year, primarily through the solar wind, an AGB star can lose mass at rates of 10 to the negative 7 or even 10 to the negative 4 solar masses per year. At the highest rates, the star is losing a substantial fraction of its remaining mass every few tens of thousands of years. This wind is not a clean, invisible breeze. It is thick, dense, and loaded with molecules and dust grains. As the material expands and cools, complex chemistry occurs in the outflow. Simple molecules like carbon monoxide form first, followed by more complex species, silicon carbide grains, aluminum oxide crystals, and carbonaceous particles condense out of the gas, forming a circumstellar envelope of dust that can completely shroud the star at visible wavelengths. Some AGB stars are so embedded in their own expelled material that they are invisible in optical light, detectable only in the infrared, where the warm dust glows brightly. These stars are in the process of destroying themselves, not through explosion, but through the steady, relentless evacuation of their own substance. The chemistry occurring in the outflows of AGB stars is remarkably rich. In oxygen-rich AGB stars, where oxygen atoms outnumber carbon in the atmosphere, the dominant dust species are silicates, minerals similar to those found in rocks on Earth. In carbon-rich AGB stars, the products of efficient dredge-up, the dust is predominantly composed of amorphous carbon and silicon carbide. These tiny grains, smaller than a micrometer in diameter, are extraordinarily important for the future evolution of the galaxy. They are the seeds around which icy mantles will form in the cold interstellar medium. They are the building blocks from which rocky planets will one day be assembled. The dust grains blown from a dying AGB star today may, in a few billion years, become part of a mountain on an alien world, or a grain of sand on a distant beach. The connection between the death of a star and the birth of a planet is physical, material, and direct. In the later stages of AGB evolution, some stars also undergo a curious transformation in which heavy elements produced by the S process are brought to the surface in particularly large quantities. These are the barium stars and the technetium stars, named after the elements that show up prominently in their spectra. Technetium is especially significant because it has no stable isotopes. The longest-lived isotope of technetium, technetium-99, has a half-life of only about 211,000 years. A blink of an eye compared to a star's lifetime. The presence of technetium in an AGB star's atmosphere is therefore proof positive that the S process is happening right now inside the star, and that the products are being dredged to the surface on timescales shorter than the decay time. It is one of the most direct pieces of evidence for ongoing nucleosynthesis in evolved stars. And it is this mass loss, not any catastrophic event, that ultimately ends the AGB star's life. Layer by layer, breath by breath, the star's outer envelope is stripped away. The hydrogen-burning shell grows ever thinner as material above it is blown into space. Eventually, the envelope becomes so thin that the shell burning can no longer be sustained. The nuclear fires flicker and die. What remains is the hot, exposed core, a ball of carbon and oxygen surrounded by perhaps a thin layer of helium and an even thinner skin of hydrogen. The star has shed its chrysalis. The transition from AGB star to what comes next is one of the most visually stunning events in all of stellar astronomy. As the dying star expels its outer layers, the ejected material forms an expanding shell, or sometimes multiple shells, of gas around the central remnant. This shell moves outward at speeds of roughly 10 to 30 kilometers per second. Faster winds from the increasingly hot central star can catch up to and compress the slower, earlier ejecta, sculpting the material into intricate patterns. Meanwhile, the exposed core is contracting and heating rapidly. Its surface temperature climbs from a few thousand degrees to tens of thousands, then to 50,000, then to 100,000 degrees or more. At these temperatures, the core emits fierce ultraviolet radiation, photons with enough energy to rip electrons from atoms in the surrounding gas. The ejected shell begins to ionize, and ionized gas glows. Different elements produce different colors. Hydrogen shines red and pink, oxygen produces blue and green, nitrogen contributes deep crimson, and sulfur adds warmer tones. This is a planetary nebula. The name is a historical artifact, a misnomer that has persisted for over 2 centuries. William Herschel, the tireless German-born English astronomer who discovered Uranus and catalogued thousands of deep sky objects, coined the term in the 1780s. Through his telescope, these objects looked like small, round, somewhat fuzzy disks, reminiscent of the distant planets Uranus and Neptune. The name stuck, even after astronomers realized that planetary nebulae have absolutely nothing to do with planets. They are the shed skins of dying stars, and they are magnificent. The Hubble Space Telescope, along with ground-based observatories, has revealed planetary nebulae in extraordinary detail, showing a breathtaking diversity of shapes and structures. The Ring Nebula in the constellation Lyra, one of the most famous, appears through a telescope as a tiny, luminous donut of gas, with a faint white dot at its center. The white dwarf that created it, the Cat's Eye Nebula in the constellation Draco, displays an almost psychedelically complex structure of concentric rings, jets, and filamentary arcs, suggesting a history of episodic mass ejection sculpted by binary interactions or magnetic fields. The Helix Nebula, one of the closest planetary nebulae at roughly 700 light-years from Earth, is sometimes called the Eye of God for its haunting appearance, a vast circular ring of gas, deep blue and turquoise at the center, fading to red at the outer edge, with a tiny white dwarf staring out from the center like a cosmic pupil. The Butterfly Nebula, also known as NGC 632, is a bipolar planetary nebula with two vast lobes of gas extending in opposite directions from a central waist. Looking remarkably like the wings of a butterfly, the central star is one of the hottest objects known, with a surface temperature exceeding 200,000 degrees. It is hidden behind a dense equatorial disk of dust, which is what gives the nebula its bipolar shape. The fast stellar wind can only escape along the poles, inflating two bubbles of gas rather than a single sphere. Not all planetary nebulae are so elaborate. Some are nearly perfectly spherical, simple, expanding shells of gas. The specific shape depends on a complex interplay of factors: the mass and rotation rate of the progenitor star, the presence or absence of a binary companion, the strength of the magnetic field, and the history of mass loss on the AGB. Recent research has strongly suggested that binary companions play a central role in shaping many, perhaps most, planetary nebulae. The gravitational influence of an orbiting companion can funnel the stellar wind into a disk, create spiral patterns, or drive bipolar jets, all of which profoundly influence the final appearance of the nebula. Regardless of their shape, all planetary nebulae share a common fate. They are transient. The expanding gas dissipates into the interstellar medium within about 10 to 20,000 years, a blink of an eye in cosmic terms. During their brief existence, though, they serve a purpose of immense importance. They are the primary means by which low and intermediate mass stars return processed material to the galaxy. The chemical enrichment provided by planetary nebulae is not a minor footnote in galactic evolution. It is a central chapter. Stars with masses between roughly 1 and 8 solar masses, the range that produces planetary nebulae, account for over 95% of all stars in the galaxy. Each one, at the end of its life, contributes its share of processed material to the interstellar medium. Over billions of years, this steady drizzle of enriched material has fundamentally changed the chemical composition of the Milky Way. The earliest stars, formed from the nearly pure hydrogen and helium left over from the Big Bang, contained almost no heavy elements. Each subsequent generation, built from material enriched by its predecessors, contains more. Our Sun, a relatively recent star born about 4.5 billion years ago, is perhaps a third-generation star. Its composition reflecting the accumulated contributions of countless stars that lived and died before it. The calcium in your teeth was forged inside a star. The oxygen in the water you drink was made in a stellar core. And much of that material passed through a planetary nebula on its way to becoming part of you. The carbon, nitrogen, oxygen, and heavier elements synthesized inside the star during its red giant and AGB phases are scattered into space by the nebula, mixing with the existing interstellar gas and enriching it for future generations of star formation. Every new star that forms, every new planet that coalesces from a circumstellar disk, is built in part from the ashes of stars that came before. Planetary nebulae are the delivery vehicles for this cosmic inheritance. The first planetary nebula ever discovered was the Dumbbell Nebula, catalogued by Charles Messier in 1764 as Messier 27. It lies in the constellation Vulpecula and is visible through even a small telescope as a bright, hazy patch of light. Its central star is one of the largest known white dwarfs. The study of planetary nebulae advanced enormously with the launch of the Hubble Space Telescope in 1990, which revealed their structures in unprecedented detail, showing fine filaments, knots, and jets that had been invisible from the ground. Each new image seemed to reveal another layer of complexity, another clue about the final moments of stellar life. Recent observations using the Atacama Large Millimeter Array, known as ALMA, have shown that the stellar winds of AGB stars are often far more complex than older models predicted. Many show spiral structures, bipolar jets, and disk-like formations, suggesting that binary companions or even large planets play a significant role in shaping the outflow. One remarkable AGB star, V Hydri, was found to be surrounded by at least 6 expanding rings of gas, along with 2 hourglass-shaped structures, painting a picture of a death that is anything but simple. It is likely that our own sun will produce a planetary nebula when it dies. The sun is not in a binary system, so simpler models would predict a relatively spherical nebula. But Jupiter and Saturn, the massive planets of the outer solar system, may exert enough gravitational influence on the sun's dying stellar wind to create a subtle spiral structure, perhaps even a faint ring pattern. 5 billion years from now, the sun's planetary nebula may glow in the skies of distant civilizations, a delicate shell of light around a tiny white dot, beautiful and transient, and utterly unaware that it was once home to a world called Earth. And when the nebula finally fades, what remains at the center is the star's ultimate legacy, a white dwarf. The object left behind is extraordinary. It contains roughly 50 to 70% of the original star's mass, but compressed into a volume comparable to the Earth. This means densities of roughly 1 million grams per cubic centimeter. A sugar cube-sized piece of white dwarf material would weigh roughly a ton. A matchbox full of it would weigh as much as a large truck. The surface gravity is about 100,000 times the surface gravity of Earth. If you could somehow stand on the surface of a white dwarf, you cannot. The gravity would crush you into a film thinner than an atom. You would weigh roughly as much as an aircraft carrier weighs here on Earth. The white dwarf is composed primarily of carbon and oxygen, the products of helium fusion during the star's earlier red giant life. Encasing this carbon-oxygen core is a thin mantle of helium, perhaps 1% of the total mass, and on top of that, an even thinner veneer of hydrogen, perhaps 1/10,000th of the total mass. These layers are stratified by gravity. The heaviest elements sink to the center, and the lightest float to the top. The atmosphere of the white dwarf is extraordinarily thin and remarkably pure. Astronomers classify white dwarfs based on the composition of their visible atmosphere. DA white dwarfs have hydrogen-dominated atmospheres and make up the majority of the known population. DB white dwarfs have helium-dominated atmospheres, and rarer types, like DQ carbon-rich and DZ metal-rich, round out the classification scheme. There is no nuclear fusion occurring inside a white dwarf. The temperature, while still high, is not sufficient to ignite carbon or oxygen fusion in the core. And without fusion, the white dwarf has no internal energy source. It glows solely because it is hot, the residual heat left over from its formation, slowly leaking out through its surface. In this sense, a white dwarf is not really a star at all. It is a stellar corpse, a remnant, a glowing ember slowly cooling in the darkness. And yet, white dwarfs are far from boring. In recent decades, astronomers have discovered that a significant fraction of white dwarfs, roughly a quarter to a third of the known population, show traces of heavy elements like calcium, iron, magnesium, and silicon in their atmospheres. This is deeply puzzling. In the ferocious gravity of a white dwarf, heavy elements should sink below the photosphere within days to millions of years, depending on the element and the star's temperature. They should not be visible at the surface. The prevailing explanation is that these white dwarfs are being actively polluted. They are accreting rocky material, likely the debris of asteroids or even small planets that wandered too close and were torn apart by the white dwarf's intense tidal forces. The shredded rocky material forms a debris disk around the white dwarf, and fragments from this disk rain down onto the surface, replenishing the heavy elements in the atmosphere. This discovery has turned white dwarfs into unexpected tools for studying the composition of extrasolar planetary material. By measuring the abundances of different elements in a polluted white dwarf's atmosphere, astronomers can effectively determine the bulk composition of the rocky bodies that were destroyed. In some cases, the compositions closely match those of the rocky planets in our own solar system. In others, they suggest exotic compositions, water-rich bodies, or differentiated objects with distinct core and mantle layers. In a remarkable twist, the deaths of stars have become windows into the geology of alien worlds. The first evidence of extrasolar planetary material was actually detected as far back as 1917, when the Dutch-American astronomer Adriaan van Manen observed calcium, iron, and magnesium in the atmosphere of a white dwarf now known as Van Manen's star. At the time, nobody understood what they were seeing. It took nearly a century for the connection to planetary debris to be made. White dwarfs have another use that makes them invaluable to astronomers. They serve as cosmic clocks because all white dwarfs cool at a predictable rate. The coolest, faintest white dwarfs in a given population are also the oldest. By measuring the luminosity of the faintest white dwarfs in a globular cluster or in the disk of the Milky Way, astronomers can estimate the age of that population with remarkable precision. The faintest white dwarfs in the oldest globular clusters have been used to independently verify the age of the universe, producing results consistent with other methods like the cosmic microwave background measurements. In 2006, the Hubble Space Telescope conducted a census of the dimmest white dwarfs in the globular cluster NGC 6397, pushing the limits of what could be detected and providing some of the tightest constraints on the cluster's age. But what prevents this incredibly dense, massive object from collapsing further under its own gravity? The answer, as we discussed earlier, is electron degeneracy pressure. the quantum mechanical resistance of electrons, governed by the Pauli exclusion principle, to being compressed beyond a certain density. The electrons in the white dwarf's interior are in a fully degenerate state. Every available low-energy quantum state is occupied. Additional compression would require forcing electrons into quantum states that are already full, which the laws of physics prohibit. This degeneracy pressure is independent of temperature. It depends only on density. So even as the white dwarf cools, the pressure holding it up does not diminish. The white dwarf can cool all the way to absolute zero in principle and still remain intact. It is perhaps the most stable long-term configuration that matter can assume. The story of how we came to understand this involves one of the most brilliant and, in some ways, tragic intellectual dramas of 20th century physics. The discovery of white dwarfs as a class of objects stretches back to the mid-1800s, when the German astronomer Friedrich Bessel noticed a wobble in the path of Sirius, the brightest star in the night sky, as it moved across the heavens. Bessel, working meticulously with the best astrometric instruments of his era, concluded in 1844 that Sirius must have an unseen companion, a small, faint star whose gravity was tugging on the brighter star. For nearly 2 decades, nobody could find this companion. It was too close to the blinding glare of Sirius itself. Then, in 1862, Alvin Graham Clark, a young American telescope maker, spotted the companion while testing a new 18.5-inch refracting lens he had just finished grinding for the Dearborn Observatory. It was a tiny, faint star nestled close to the brilliant blue-white blaze of Sirius A. It was later named Sirius B when its mass was eventually measured, roughly equal to the Sun, and its size estimated roughly equal to the Earth. The implications were staggering. The density was unlike anything ever encountered, about 25,000 times the density of steel. The discovery was met with disbelief. Arthur Eddington, the leading astrophysicist of the early 20th century, captured the bafflement of the scientific community with characteristic wit. He paraphrased the message of Sirius B as something like, "I am made of material thousands of times denser than anything you have ever encountered. A ton of my material would be a small nugget you could put in a matchbox." And he noted that the common reaction among scientists at the time was essentially, "Do not talk nonsense." But it was not nonsense. It was quantum mechanics. The first step toward understanding white dwarf matter came with the work of Ralph Fowler, a British physicist who, in 1926, applied the newly developed Fermi-Dirac statistics to the problem. Fowler showed that the extreme density of white dwarf material could be explained by the quantum mechanical properties of electrons in a degenerate state, a gas in which the Pauli exclusion principle dominates the behavior of the particles. The electrons, stripped from their atoms and packed into an impossibly small volume, generate a pressure that has nothing to do with temperature and everything to do with the fundamental nature of quantum mechanics. The term white dwarf itself was coined by the Dutch-American astronomer Willem Leiden in 1922, reflecting their small size and their typically white or blue-white color when first formed. Over the decades, the census of white dwarfs has grown enormously. Galactic models suggest the Milky Way currently contains approximately 10 billion white dwarfs, making them one of the most numerous types of stellar remnant in the galaxy. 8 white dwarfs are known among the 100 star systems nearest to the Sun. They are everywhere, surrounding us in all directions, silent and dim, but utterly ubiquitous. And then came Chandrasekhar, Subramanian Chandrasekhar, traveling by ship from India to Cambridge in 1930, combined Fowler's quantum mechanical treatment with special relativity. At the extreme densities inside the most massive white dwarfs, the electrons are forced to such high energies that they approach the speed of light. Chandrasekhar showed that relativistic effects change the equation of state of the degenerate electron gas, weakening its ability to resist compression. There exists a critical mass, about 1.44 times the mass of the Sun, beyond which the degeneracy pressure of even relativistic electrons is insufficient to counteract gravity. This is the Chandrasekhar limit. For white dwarfs below this limit, the star is stable. It will cool over cosmological timescales, gradually fading but never collapsing. For stellar remnants above this limit, something else must happen. The electrons cannot hold up the star. Further collapse is inevitable, leading to a neutron star, where neutron degeneracy pressure takes over. Or, for even more massive remnants, a black hole, where no known force can resist gravity. The Chandrasekhar limit is one of the most important numbers in all of astrophysics, a boundary between the familiar and the exotic, between a gentle death and a violent one. When Chandrasekhar presented his findings at a meeting of the Royal Astronomical Society in 1935, Eddington publicly attacked the work, declaring that he believed there should be a law of nature preventing a star from behaving in such an absurd way. The confrontation was harsh and deeply humiliating for the young Indian physicist. Eddington was one of the most respected scientists in the world, and his dismissal carried enormous weight. Many astronomers sided with Eddington, not necessarily because they found flaws in Chandrasekhar's mathematics, which were impeccable, but because the implications seemed too strange to accept. Chandrasekhar, discouraged but not defeated, eventually moved on to other areas of astrophysics. He would go on to make groundbreaking contributions to radiative transfer, stellar dynamics, and the mathematical theory of black holes, becoming one of the most productive and wide-ranging astrophysicists of the 20th century. But the sting of Eddington's public rebuke stayed with him throughout his career. Over the following decades, observation after observation confirmed his limit. Every directly measured white dwarf mass fell below 1.44 solar masses. The Chandrasekhar limit became one of the foundational pillars of modern astrophysics, as fundamental to our understanding of stellar death as the Hertzsprung-Russell diagram is to our understanding of stellar life. In 1983, more than 50 years after his solitary calculations aboard a ship at sea, Chandrasekhar shared the Nobel Prize in Physics with William Fowler for their respective contributions to understanding stellar structure and evolution. The name Chandrasekhar lives on not only in the limit that bears his name, but also in the Chandra X-ray Observatory, a NASA space telescope launched in 1999 that continues to study the most extreme objects in the universe, many of which owe their existence to the physics Chandrasekhar first described on that long sea voyage. A newly born white dwarf starts life at a ferocious temperature, Well, over 100,000 degrees at its surface, perhaps 100 million degrees in its core. It bathes the surrounding space in ultraviolet radiation and X-rays, lighting up whatever planetary nebula still surrounds it. But without a source of internal energy, it can only cool, and so begins the longest chapter of the white dwarf's existence. A slow, gentle, almost meditative decline toward absolute cold. The physics of white dwarf cooling is elegant and somewhat counterintuitive. The degenerate interior of the white dwarf has very high thermal conductivity. Heat flows through it easily and rapidly, keeping the interior at a nearly uniform temperature. The bottleneck for cooling is the thin, non-degenerate outer envelope, which acts as an insulating blanket. Heat must diffuse through this envelope before it can be radiated into space, and the envelope's opacity controls the rate at which energy escapes. As the interior cools, the luminosity drops, and the surface temperature decreases. Over billions of years, the white dwarf dims from a brilliant blue-white to a cool, faint red, and eventually, in theory, to a completely dark object emitting no detectable radiation at all. But the cooling process is not perfectly smooth. At certain temperatures, the ions in the white dwarf's interior undergo a phase transition. Remember, the interior starts out as an extremely hot liquid, carbon and oxygen nuclei swimming freely in a sea of degenerate electrons. As the temperature drops, the thermal energy of the ions decreases. Eventually, the electrostatic forces between the positively charged ions become dominant over their thermal motion, and the ions lock into a regular, repeating geometric arrangement. The interior crystallizes, transitioning from a liquid to a solid state, just like water freezing into ice. But this is not water ice. It is crystalline carbon and oxygen, arranged in a lattice structure at pressures and densities far beyond anything achievable in any laboratory on Earth. This crystallization process releases latent heat, the same way that freezing water releases heat into its surroundings. This extra energy temporarily slows the cooling of the white dwarf, causing it to linger at certain luminosities longer than it otherwise would. In 2019, a team of astronomers analyzing data from the European Space Agency's Gaia satellite, which had precisely measured the properties of hundreds of thousands of white dwarfs, found unmistakable evidence of this crystallization-induced cooling delay. They identified a clear pileup in the cooling sequence, an excess of white dwarfs at specific luminosities and temperatures that exactly matched the predictions for crystallization. It was a beautiful confirmation of a theory that had been proposed decades earlier, but never observationally verified at this scale. The crystalline form of carbon, of course, is diamond, and while the conditions inside a white dwarf are very different from those inside the Earth's mantle, where natural diamonds form, the fundamental process is similar. Carbon atoms, under immense pressure, arrange themselves into a crystal lattice. Astronomers have sometimes referred to these crystallizing white dwarfs as cosmic diamonds, Earth-sized objects composed of solidified carbon, drifting through the galaxy. The white dwarf BPM 37093 in the constellation Centaurus, nicknamed Lucy after the Beatles' song, was one of the first for which direct evidence of crystallization was found through the study of its pulsations. More recently, HD 190,412c, just 104 light-years away, was identified as a crystallizing white dwarf whose age could be independently constrained by the other stars in its quadruple system, providing an important benchmark for testing crystallization models. Given enough time, vastly more time than the current age of the universe, a white dwarf will cool completely. Its temperature will drop to just a few degrees above absolute zero. It will emit no visible light, no infrared radiation, nothing detectable. It will become a black dwarf, a cold, dark, invisible sphere of crystallized carbon and oxygen, roughly the size of the Earth, carrying roughly the mass of the Sun, drifting forever through the void. No black dwarf exists yet. The universe is far too young. The coolest known white dwarfs still have surface temperatures of about 3,000 to 4,000 degrees Celsius, warm enough to glow a faint, deep red. These are among the oldest objects in the cosmos, remnants of some of the first stars that ever formed. And even they have barely begun their long journey toward darkness. The estimated time for a white dwarf to cool to a black dwarf state is on the order of 10 to the 15th years, a quadrillion years. For comparison, the universe is about 14 billion years old, or roughly 10 to the 10th years. A quadrillion is 100,000 times larger. The universe would have to age 100,000 times over before the first black dwarfs appeared. It is a timescale so vast that it staggers comprehension. The entire history of the universe so far, from the Big Bang through the formation of galaxies and stars, planets and life, is a mere rounding error compared to the time a white dwarf needs to go fully dark. And yet, it is the fate that awaits every white dwarf, including the one that our sun will become. There is a haunting elegance to this final chapter of a star's life. A white dwarf, having been born in the fires of nuclear fusion, having endured the upheavals of the red giant phase and the shedding of its outer layers, finally finds itself in the most stable configuration that physics allows. It sits in a state of near-perfect equilibrium, held together by gravity and held apart by the quantum stubbornness of electrons. It does nothing. It consumes nothing. It creates nothing. It merely radiates the last of its stored heat into the cosmos, growing imperceptibly cooler with each passing epoch. It is the universe's most patient object, waiting out the ages with a composure that no living thing could ever match. And in the far, far future, long after the last star has been born and burned out, long after the galaxies have dispersed and the cosmos has entered its final age of darkness, the white dwarfs will still be there, silent, cold, invisible, the last material remnants of the age of stars, drifting through an empty universe, carrying within their crystallized cores the record of stars that once burned bright. But this is the story of a solitary white dwarf, cooling alone in the emptiness of space. Many white dwarfs do not end their days in such quiet solitude. A substantial number exist in binary systems, orbiting close to another star. And for these, the quiet afterlife of the white dwarf can be interrupted, sometimes gently, sometimes with extraordinary violence. If a white dwarf orbits close enough to a companion star, particularly a red giant with its distended, loosely bound outer atmosphere, the white dwarf's intense gravity can begin to strip material from the companion. hydrogen-rich gas flows across the gap between the two stars, spiraling down onto the white dwarf in a swirling accretion disk. As this material piles up on the white dwarf's surface, it is heated and compressed by the enormous surface gravity. The conditions at the base of this accumulated layer grow steadily more extreme. Eventually, the temperature and density become sufficient for the hydrogen to ignite in a flash of thermonuclear fusion. The surface of the white dwarf briefly becomes a hydrogen bomb, detonating in a blaze of light that can increase the system's brightness by a factor of 50,000 or more in a matter of hours. This is a nova. The word, from the Latin for new, was coined by ancient and medieval astronomers who saw what appeared to be a new star suddenly blazing in the sky where none had been visible before. Of course, the star was always there. It was simply too faint to see without a telescope. The nova explosion blows the accumulated hydrogen off the surface of the white dwarf, sending it flying into space in an expanding shell. But the white dwarf itself is unharmed. It is far too dense and too tightly bound by gravity to be disrupted by a mere surface explosion. And so, after the nova subsides, the accretion process resumes. Material flows from the companion, accumulates on the surface, heats up, and eventually detonates again. Some binary systems produce recurrent novae, repeating the cycle every few years or decades. The historical record is sprinkled with observations of novae, even if the observers did not understand what they were seeing. Chinese, Korean, and Japanese court astronomers kept careful records of guest stars appearing suddenly in the sky, dating back over 2,000 years. Some of these guest stars were undoubtedly novae, others were supernovae, which we now understand to be an entirely different phenomenon. The distinction between the two was not clearly understood until the 20th century, when astronomers like Walter Baade and Fritz Zwicky proposed that supernovae represent a fundamentally different and far more energetic class of stellar explosion. One particularly famous nova occurred in the year 1934, when a star in the constellation Hercules, later designated Nova Herculis, brightened dramatically, becoming one of the brightest stars in the sky for a time. Subsequent observations revealed the expanding shell of ejected material, and the system became a benchmark for studying the nova phenomenon. More recently, Nova Cygni in 1992 provided detailed observations across many wavelengths, helping astronomers refine their understanding of the thermonuclear processes on white dwarf surfaces. But novae, dramatic as they are, pale in comparison to the main event. If the accretion process continues long enough or proceeds rapidly enough, the white dwarf can approach the Chandrasekhar limit. As its mass creeps toward 1.44 solar masses, the conditions in the core begin to change. The carbon and oxygen in the interior, dormant for perhaps billions of years, begin to feel the rising pressure and temperature. When the core conditions cross a critical threshold, carbon fusion ignites. Not gently, not in a controlled manner, but in a catastrophic thermonuclear detonation that consumes the entire star. Alternatively, two white dwarfs in a very tight binary system may spiral toward each other, their orbits decaying through the emission of gravitational waves. When they finally collide and merge, the combined mass can exceed the Chandrasekhar limit, triggering the same thermonuclear catastrophe. This is a type Ia supernova. It is a fundamentally different beast from the core collapse supernovae that mark the deaths of massive stars. A core collapse supernova leaves behind a neutron star or a black hole. A type Ia supernova leaves behind nothing at all. The white dwarf is completely and utterly destroyed. Every atom in its body is blasted apart, fused into heavier elements like nickel, iron, silicon, and sulfur, and ejected into space at speeds of 10,000 kilometers per second or more. The explosion is so bright that, at its peak, a single type Ia supernova can outshine the entire galaxy in which it resides. Hundreds of billions of stars, all together, are dimmer than this one detonating white dwarf. The physics of the explosion itself is a subject of intense, ongoing research. For decades, the standard picture was straightforward. A white dwarf accretes material from a companion until it reaches the Chandrasekhar limit, at which point carbon fusion ignites at the center, and a detonation wave propagates outward, obliterating the star. This is called the single degenerate model. But observations in recent years have cast doubt on this simple picture. In 2011, the type Ia supernova SN 2011 Phi exploded in the nearby Pinwheel galaxy, close enough and detected early enough that astronomers could search for the companion star that should have been present in the single degenerate scenario. No companion was found. This and other observations shifted attention to an alternative model, the double degenerate scenario, in which two white dwarfs in a tight binary system spiral together and merge. If their combined mass exceeds the critical threshold, the merger triggers the detonation. In some versions of this model, called the D6 scenario, short for the tongue-twisting dynamically driven double degenerate double detonation, one white dwarf steals helium from the other, triggering a helium detonation on the surface that sends a shockwave inward to ignite the carbon core. Computer simulations have only recently been able to reproduce type Ia light curves from this double degenerate model, giving it a crucial boost of credibility. The precise mechanism matters, not just for understanding stellar physics, but for the reliability of type Ia supernovae as cosmic measuring tools. If different explosions are caused by different mechanisms, perhaps the single degenerate route in some cases and the double degenerate route in others, there might be subtle systematic differences in their brightnesses that could introduce errors into cosmological distance measurements. This is an active area of investigation, with large surveys planned to study thousands of type Ia supernovae at ever greater distances and with ever greater precision. And here is why this matters beyond the spectacular fireworks. Because type Ia supernovae are triggered at a specific, well-defined mass threshold, the Chandrasekhar limit, their peak brightnesses are remarkably uniform. Not identical, but predictable. Astronomers discovered in the early 1990s that by measuring how quickly a type Ia supernova fades after peak brightness, they could determine exactly how luminous the explosion was at its peak. Bright supernovae fade slowly, faint ones fade quickly. This relationship, known as the Phillips relation, transformed type Ia supernovae into precise cosmic distance indicators, standard candles, by measuring the apparent brightness of a type Ia supernova, a faraway, faint-looking one, and comparing it to to the known intrinsic brightness determined from the fade rate. Astronomers could calculate how far away the supernova was with impressive accuracy. This was the tool that two competing teams of astronomers, one led by Saul Perlmutter at Berkeley and the other by Brian Schmidt in Australia, used in the late 1990s to measure the expansion rate of the universe at different epochs in cosmic history. They expected to find that the expansion was gradually slowing down, decelerating under the gravitational pull of all the matter in the universe. Instead, they found the opposite. The distant type Ia supernovae were fainter than expected, meaning they were farther away than they should have been in a decelerating universe. The universe was not slowing down. It was speeding up. This discovery, announced in 1998 and honored with the Nobel Prize in Physics in 2011, is one of the most astonishing in the history of science. It implies the existence of a mysterious component of the universe, now called dark energy, that makes up roughly 68% of the total energy content of the cosmos and drives the accelerating expansion. We do not know what dark energy is. We do not know why it exists. We do not know whether it has always been the same strength or whether it is changing over time. These are among the most profound open questions in modern physics. What we do know is that the tool that revealed it, the standard candle of type Ia supernovae, has its origins in the humble white dwarf. The very same electron degeneracy pressure that holds up a quiet, cooling stellar remnant is what sets the Chandrasekhar limit. And the Chandrasekhar limit is what makes the explosions so uniform. Quantum mechanics, working at the scale of individual electrons, determines the brightness of explosions visible across billions of light years. It is a connection that spans an almost inconceivable range of scales, from the subatomic to the cosmological. And it is one of the most beautiful examples of unity in physics. NASA's Nancy Grace Roman Space Telescope, planned for launch in the near future, will survey thousands of distant type Ia supernovae, pushing the measurements to even greater distances and precision. The goal is to trace the history of cosmic expansion in finer detail than ever before, mapping out how dark energy has behaved over the last 10 or 12 billion years. If dark energy turns out to be truly constant, it confirms the simplest models. If it is changing, it opens the door to entirely new physics. And either way, the measuring sticks will be the same. The corpses of dead stars, white dwarfs pushed beyond their breaking point, telling us about the fate of the universe with their light. And so we arrive, at last, at the future of our own sun. The sun is currently about 4.5 billion years old. It has approximately 5 billion years of main sequence hydrogen burning remaining. During that time, it will gradually brighten, growing roughly 10% more luminous every billion years. In about 1 billion years, that extra brightness will be sufficient to raise Earth's average temperature enough to trigger a runaway greenhouse effect. The oceans will begin to evaporate. Within a few 100 million years after that, the surface will become too hot for liquid water to exist anywhere. Earth will become a dry, scorched world, its atmosphere thick with water vapor, and eventually stripped bare by the increasingly active solar wind. Life as we know it, at least on the surface, will be long gone. In roughly 5 billion years, the sun's core will exhaust its hydrogen. Shell burning will begin. the sun will swell into a red giant, its radius expanding perhaps to 250 times its current size. Mercury will be consumed first, its small, rocky body vaporized as the expanding atmosphere overtakes its orbit. Venus will follow, swallowed whole. The fate of Earth is less certain, but most recent models suggest that as the sun expands, tidal interactions between the expanding star and our planet will cause Earth to spiral inward, ultimately to be engulfed and vaporized within the sun's outermost layers. Even if Earth somehow survives by moving outward as the sun loses mass, it will be a bare, molten rock, its atmosphere long since burned away. Any oceans long since boiled into space, orbiting inside the diffuse, outer regions of a bloated, dying star. The view from the outer solar system during this time would be extraordinary and eerie. Where the sun once appeared as a small, bright disk, it would now fill an enormous portion of the sky, a vast, glowing dome of deep orange red light. Its surface would ripple and churn great convective cells, rising and sinking across a face millions of miles wide. The light reaching the outer planets would be cooler in temperature, but far more abundant in total energy. Frozen moons would begin to thaw. Ice would sublimate into vapor. Surfaces that had been locked in darkness and cold for billions of years would, for the first time, feel warmth. But the outer solar system will experience a strange kind of rebirth. As the sun's habitable zone shifts outward, worlds that are currently frozen wastelands could become temperate, if only briefly. Jupiter's moon Europa, with its subsurface ocean of liquid water, could develop a thin atmosphere of water vapor as the ice on its surface melts and sublimes. Saturn's moon Titan, already sporting a thick atmosphere and lakes of liquid hydrocarbons, could see its frozen surface warm enough for liquid water to exist. Models suggest Europa could maintain potentially habitable surface conditions for several 100 million years during the red giant phase. A window that, while short by geological standards, is comparable to the time it took life on Earth to progress from simple single-celled organisms to the first multicellular creatures. Even the icy bodies of the Kuiper Belt, Pluto and its neighbors, could experience surface conditions not unlike a warm day on present-day Earth. The astronomer Alan Stern has suggested that when the sun becomes a red giant, the temperatures at Pluto's distance will be equivalent to those in tropical locations on Earth. For a few 100 million years, the outer reaches of the solar system could become the most hospitable region, a strange inversion of the current order of things. Whether life could actually arise in such a brief window is an open question, but the possibility is tantalizing. It suggests that habitable conditions are not unique to the main sequence phase of a star's life, and that the universe may have many more opportunities for biology than we currently recognize. Eventually, of course, this second spring in the outer solar system will end. The sun will shed the last of its envelope, the planetary nebula will form, and the white dwarf will be revealed. The brief warmth will fade, and the outer moons and dwarf planets will freeze once more, this time permanently. The sun will spend roughly 1 billion years in various red giant phases, burning hydrogen and then helium in shells around its growing core. It will experience the helium flash, settle onto the horizontal branch, exhaust its core helium, ascend the asymptotic giant branch, pulsate with thermal pulses, dredge carbon to its surface, and shed its outer layers in an increasingly intense stellar wind. Eventually, it will expel its envelope entirely, revealing the hot carbon-oxygen core within. The total mass loss during these phases will be substantial. The Sun will shed roughly half of its current mass, perhaps a bit less, during the red giant and AGB phases. Most of this material will be expelled relatively gently, carried away by the stellar wind over hundreds of millions of years. But in the final stages of the AGB, the mass loss rate will spike dramatically. The so-called superwind phase, lasting perhaps only 10 or 20,000 years, will strip the last remaining envelope material and expose the core. This superwind is driven partly by radiation pressure on dust grains that condense in the cooling outer atmosphere, and partly by pulsation-driven shockwaves that rhythmically accelerate the gas outward. A planetary nebula will bloom around the dying sun, glowing with the ionized light of hydrogen, helium, oxygen, and nitrogen. It will be beautiful, perhaps taking on the form of a ring, or an hourglass, or a butterfly, shaped by the gravitational influence of Jupiter and Saturn, and whatever other bodies remain in the system. For perhaps 10 or 15,000 years, this nebula will expand and glow, a memorial to the star that created it, visible to any telescope pointed in the right direction from across the galaxy. And at the center of that nebula, the Sun's white dwarf will begin its long, quiet decline. It will contain roughly half of the Sun's original mass, perhaps 0.54 solar masses, according to some models, compressed into a sphere roughly the size of the Earth. It will start at a surface temperature of perhaps 100,000 degrees, blazing with ultraviolet light. Over the next several billion years, it will cool to the point where it shines with a faint yellow glow, then a dim orange, then a deep red. The remaining planets, Jupiter, Saturn, Uranus, and Neptune, whose orbits expanded to roughly twice their current distances by the Sun's mass loss, will continue to circle this tiny remnant in the darkness. They will be cold, receiving virtually no heat from the fading dwarf, illuminated only by the faint light of distant stars. The Milky Way itself will have changed by then. In roughly 4.5 billion years, our galaxy is expected to collide and merge with the Andromeda galaxy, creating a larger elliptical galaxy that astronomers have speculatively named Mulcometa. The Sun will still be on the main sequence when the collision begins, but by the time it becomes a white dwarf, the merged galaxy may be well established. The white dwarf that was once our Sun will drift through this new, larger galaxy, a cold relic of a star that shone in a spiral arm that no longer exists. Over trillions and quadrillions of years, the white dwarf will crystallize from the inside out. Its core will solidify into a cosmic diamond, a sphere of crystallized carbon the size of the Earth, carrying the compressed legacy of 4.5 billion years of stellar life. And eventually, so far in the future that the number of years required would fill pages with zeros, it will cool to absolute zero and become a black dwarf. Invisible, inert, floating silently through a universe that has itself grown old and cold. But this is not truly an ending. The material that the Sun expelled during its death, the carbon, oxygen, and nitrogen forged in its nuclear furnace, will mix into the interstellar medium. it will drift through the galaxy, enriching molecular clouds with the heavy elements needed to build rocky planets and organic molecules. Billions of years after the sun's death, some of that material may find its way into a new collapsing cloud, a new protostar, a new solar system. New planets may form, new oceans may fill, and perhaps in some distant world, under the light of a star that does not yet exist, new life may arise, built from the very atoms that once burned inside our sun. The universe is, at its heart, a vast engine of recycling and renewal. Stars are born from the debris of their predecessors. They live, they create new elements through nuclear fusion, and they die, scattering those elements back into the cosmos. Each generation of stars is richer in heavy elements than the last, building complexity upon complexity. From the simplest hydrogen and helium all the way up to the iron in your blood, the calcium in your bones, the carbon in your DNA, the gentle deaths of sun-like stars, the bloating into red giants, the shedding of luminous planetary nebulae, and the quiet cooling of white dwarfs are essential chapters in this ongoing story. Without them, the universe would be a far simpler, far emptier, and far less interesting place. Consider the sheer number of stars involved. Astronomers estimate that the Milky Way galaxy contains roughly 10 billion white dwarfs. 10 billion. Each one is the remnant of a star that lived, burned through its hydrogen, swelled into a red giant, shed its outer layers, and settled into a quiet retirement that will last longer than the current age of the universe. Each one enriched the galaxy with heavy elements during its death. Each one contributed to the chemical complexity that makes planets, oceans, and life possible. The white dwarfs drifting through the galaxy are not merely dead stars. They are monuments to the generative power of stellar evolution, tombstones that also serve as cornerstones for the next cycle of creation. And not all of these stories are finished. White dwarfs in binary systems continue to interact with their companions, producing novae, occasionally detonating as type Ia supernovae, shaping the chemical evolution and the energy budget of the galaxy. Even solitary white dwarfs, through their gravitational interactions with surviving planetary systems, tidally disrupting asteroids and accreting rocky debris, are telling us about the architecture of planetary systems that we can study in no other way. The deaths of stars are not endpoints. They are transitions, doorways from one chapter of the cosmic narrative to the next. It is humbling and also deeply beautiful to realize that the atoms in your body have been on this journey before. They were inside a star. They were expelled when that star died. They drifted through space, perhaps for millions of years, before being swept up into the collapsing cloud that became our solar system. They coalesced into a planet. They became part of an ocean, a rock, a living cell. And now they are part of you, reading these words, contemplating the lives and deaths of stars. Someday, billions of years from now, those same atoms will be inside another star, continuing the cycle. You are not merely an observer of the cosmos. You are a participant in it, made of its stuff, carrying its history in every cell of your body. So the next time you look up at the night sky and see the warm orange glow of Arcturus, or the ruddy eye of Aldebaran, or the pulsating heartbeat of Myra, know that you are watching this ancient story unfold in real time. Those stars are in the process of dying, right now. As you watch, the carbon and oxygen they are creating will one day be scattered across light years of space. And some of those atoms, trillions of years from now, may end up inside a living being on a world we cannot imagine. A being who will look up at the stars and wonder, just as you do, how it all began. The universe tells its story through the lives and deaths of stars. And the slow, gentle deaths of sun-like stars, from the first quiet flicker of hydrogen fusion in a newborn core, to the last fading glow of a crystallizing white dwarf in the eternal dark, are among the most beautiful chapters in that never-ending story. Thank you so much for watching. If you enjoyed this video, please do leave a like and subscribe to the channel. We would love to hear your thoughts in the comments below. Let us know what you found most fascinating or what topics you would like us to explore next. Until then, keep looking up, and we will see you next time.